Okay, so the idea behind experimental design is we are trying to demonstrate a functional relationship between our treatment and the effects on behavior. So we do our treatment, we collect data, we follow the data to see if we're helping the subject. We have to be able to show scientifically, experimentally, that we are in fact contributing to the changes we see, but not just happening randomly. So we basically take the scientific method where we're going to use the three foundations of science: prediction, description, and control. You're going to describe the phenomena that you're studying. You're going to then predict what would happen if you were to manipulate some variables that affect that subject area. And then you're going to manipulate and control those variables. Describe, predict, control what would happen if, in fact, what you are doing is going to affect the performance of your subject. In our case, we're looking at behavior. So we want to describe a behavioral phenomena, define the behavior, measure it, get a baseline. Then we're going to develop a treatment. And then we're going to do that treatment and see if that behavior changes. So we're trying to determine if our treatment functions to make more or less behavior. Does our treatment, does our behavior plan, does our therapy change the behavior? If we have a missing behavior, can we teach it and increase that behavior in the repertoire of our client? If we've got a problem behavior, can we develop a treatment and change that so the problem behavior happens less often? Can we make it better for the client? And can we say that it's due to our treatment? Is it a function of what we've done? So we have the basic scientific process, and I can send you all this picture that I've taken. So rather than read all of this to you, you can practice this on your own. I want to hit the main points because we only have an hour, and this is a 6-hour lecture. So our driving premise is that experimental design for behavior analysis is that behavior is a function of the environment. So we're looking at antecedents and consequences affecting behavior. Schedules of reinforcement, how consequences make more behavior. If it's reinforcing, make less behavior when it's punishing. Or if you're reinforcing behavior and you stop, you get less behavior later when the extinction kicks in. So we're talking about the significance of the treatment. Does it really make a significant difference? Does it even make a difference? One of the premises is that the null hypothesis, null mean nothing, says nothing you do really changes it. It's going to happen anyway. And so what we're doing is we are testing the alternate hypothesis, where we are hypothesizing that our treatment will indeed bring about a change in the performance of the subject. The behavior, the dependent variable, how they behave, depends on how they're treated. And the independent variable is the treatment. So the treatment is whether we're giving stickers or stars or praise. The independent variable is our protocol, our treatment model or intervention. And the dependent variable is how the subject behaves, whether they do something longer or more times, etc. Now, the statistical analysis is the common gold standard for group design. People are randomly assigned. One group gets treatment, one group is a control group. They test them before, they test them after, and they compare the results. And then they do analysis of variance and covariance and Fisher two-tailed t-test, all kinds of mathematical formulas to try to control for variance. And then when you're done, you look it up in a chart to see if it's statistically significant. That your treatment would have changed. So what's the probability? You would get a probability of 0.05 chance of treatment make an effect, or probability of 0.1. That's a whole other area, and that's more psychology and more social sciences. We're dealing with single subject, so we're looking for clinical and social significance. Are we solving a social problem for the client, for the family, for the teacher, for the school, for the community? And is our clinical procedure significant? Are we really bringing about the change that we're supposed to bring about? Our target, we have our goals and our targets. So we're looking at a single subject design, not group. And what we do with the single subject design is we're going to get repeated measures. We're going to get measured the same behavior over and over and over. We'll measure during baseline. We're going to measure it during treatment. And we want to see if there's any variability. If the data is bouncing around, we don't want to start to try to treat it. We want to make sure that the behavior is fairly stable in the environment during baseline. Then as we bring about changes, the subject will be their own control for whether or not they change behavior versus the control group, because we're not treating the control group. So again, we're single subject. Experimental designs will be addressing how this single person does in treatment. That's our giant process. We have to be able to look at the data and interpret it. So we interpret data based on the level of behavior. Is it a medium, low, medium, or high level of behavior? Is there a trend? Is it a flat trend? Is it stable? Or is it trending upwards, or is it trending downwards? And we're going to look at variability. How much is the behavior bouncing around? If it's bouncing around a lot, then it's not under good experimental control. If it's fairly stable, it should represent that the treatment is making those changes. So one of the ways we interpret data is we look at the baseline, we do our treatment, and then we analyze, and we call it a visual analysis, because we're going to do an eyeball analysis. We're going to look at it and see what the data looks like. Is the level, trend, or variability, are those changing? Now, an important argument for us to show that it's a functional relationship is to use what's called baseline logic. We're going to describe the behavior. We're going to predict what it would do without treatment. We're going to then verify that it did or did not change from the prediction. And then we're going to see if we can replicate the change and make it happen by putting the treatment in and taking the treatment out. Can we do something to show the change is, in fact, due to the treatment? Once again, we're trying to show a functional relationship between the presence of the treatment and the behavior. So back to the science of description, prediction, control, we're going to have independent and dependent variables. The independent variable is the treatment, how you treat the subject, and the dependent variable is the performance. How they perform depends on how they're treated. The treatment might be as simple as a sticker or a star or praise. Could be a token economy system, something that we've done that isn't regularly happening. Something that's not happening in baseline, we're going to introduce it. So our key concepts are experimental control to show that it changes when and only when we do the treatment. We're going to manipulate the treatment to show the presence of treatment makes behavior change, and you pull out the treatment and it changes back. So that's the independent variable. We're going to measure those changes by taking the definition, collecting baseline, do the treatment, and look to see if that measure, are they doing more behavior or behavior longer? And that's the dependent variable. We're looking for the functional relations to see, does the treatment function to make the behavior change? Whether it goes up or down is a social value, and that's important, but we're really looking experimentally is, did it change due to the treatment? Can I eliminate that it just happened randomly? So we have to interpret the data with baseline logic. We're going to use the visual analysis. It needs to be pragmatic. It needs to make sense. It needs to be practical. We want to look at the designs and see the strength of a design and the weakness of a design. We want to know the difference between internal and external validity. Internal validity is within the treatment for the subject. Does it make sense? Is it changing? External validity is, can I take the same treatment to other subjects and can I get the same results with them external to this environment with this subject to another set of subjects? Does my treatment really generalize? Will it affect someone else besides the one I treated? So I have within subjects designs. So how within the design are my change conditions? Are they going to affect the subject? I'm going to have between subjects without in not just the subject, between other different people. These are some of the terms you're going to run into. You want to look them up and study them. Now to go to design. I mentioned level, trend, and variability. So these graphs would show, here's a level behavior, say it's kind of low, and we see that it's starting to go up, so we see an increasing trend. Here, the other one, we have behavior up around the high end, and we see it dipping down and then a decreasing trend. And the bottom one, we basically have behavior at about a medium level, and it's fairly stable. So we'd say there was no trend. It's not trending, it's stable. What we would call that is a steady state of responding. If we're going to treat behavior, we don't want to start if it's bouncing around. We want to start with a steady state. So this next design is going to show baseline logic. And here's baseline with a fairly stable low rate of behavior. It's not trending up or down. One way to look for the trend is if I look at the number of data points and I could draw a line with half of the points above the line and half of the points below, I could see if that line is fairly flat, or if I drew the line with half above and below, I could see that it was trending up. Or if I took and draw a line between and saw, I could see if it's trending down. So if I was drawing a straight line with half the points above and half the points below, it gives me an idea of the trend. Now, baseline treatment means this is everything the subject has happened in the world. This is their reinforcement, their punishment history. This is everything in life until you walk in with your treatment. Baseline logic says the prediction is, with the null hypothesis, what you do doesn't matter, it's not going to change it. So the prediction is it should stay right there at the baseline level. Your alternate hypothesis is that if I give this kid stickers for cooperating, he's going to give me more behavior, more cooperative behavior. So if I've got a child whose his baseline of being in his seat in the classroom is low, and my hypothesis is he might stay in his seat if he can earn stickers, I'm going to measure the behavior of in seat, and I see it's low, and then I'm going to try to increase it. So I give him stickers and I collect the data. And now I can see that from baseline to treatment, the actual behavior did change. It went from a low level, and now it's at a high level. Prediction was it wouldn't have changed. So I'm going to argue that the presence of treatment had an effect on this behavior. I cannot yet claim a functional relationship because it could have gone up coincidentally. Could have been just for some reason at that time he decided to start sitting in his seat more. So I have to continue with my experiment. Now, this is a single element design because I have one single treatment. This is baseline phase. This is phase number 2. This is my treatment phase. In my third phase, I'm going to go back to baseline where I'm going to stop giving him stickers for being in his seat. Now, the prediction will be, since it changed anyway, not because of me. That's the null hypothesis. The prediction is it changed, so it should stay up there if I'm going to use the null hypothesis. My alternate was it changed because of treatment. So I take the treatment out, I withdraw the treatment, and if the behavior goes down, I've now verified that the presence of treatment changed the level of behavior, and the absence of treatment, it changed again. So now I've used prediction to show that the change did occur. I used prediction again, and since I took treatment out, I can now verify that the presence of treatment had an effect on the rate of responding. Now, the next thing I have to do, and since it came down again, the prediction is it would stay there. Null hypothesis, it would stay there. But I did put the treatment back in. I reinstated the treatment, and now I've replicated the effect. So I have prediction, verification, and replication as baseline logic. And now with these conditions, I can say there is a functional relationship between the presence of treatment, the independent variable, and the level of behavior. So this behavior changes when and only when I put in my treatment. That's part of my functional relationships. And this is a single design. It's called an ABAB. Some people call it a return to baseline design because in baseline there was no treatment for the target behavior. And then in the baseline 2, there was no treatment for target behavior. If the target behavior is in seat and the in seat changed, and then I stop that treatment, and it drops back down, I'm back to baseline conditions. They call it withdrawal because I withdrew my treatment. There's another name for this design. You may see one called a reversal design. And a reversal design is the same as an ABAB withdrawal design. The difference is what I would do with the reversal. This is a very picky difference, but it's important. I would reinforce the child for in-seat behavior with a sticker. And then during this baseline, I would stop reinforcing in-seat behavior, so that's withdrawal of the treatment, but I would be giving the child stickers for out-of-seat behavior, which is a reversed contingency. Here the contingency was be in your seat, get a sticker. Now I've changed the contingency, be out of your seat, get a sticker. And if my treatment is real powerful, he will now be out of his seat, which means the in-seat behavior data goes down, but it's actually due to the fact that I'm reinforcing the opposite behavior. So that's called a reversal because I've reversed the direction of the behavior for the target behavior by treating an opposite behavior. So that's what they mean by reversal. You reverse the contingency. So this same design is an ABAB. It's called withdrawal design. You may hear about return to baseline, which means return to baseline conditions with no treatment for the target behavior. You may hear about a reversal design where you're reversing the contingency, but there's still no treatment for the target behavior. And that's an ABAB design. So a quick review, baseline and treatment is a two-phase design. It's an AB design. The strength of this is that it shows there was a change. The weakness is I cannot claim a functional relationship until I demonstrate that the behavior goes back when I stop the treatment. Here's a second graph, and you'll see here's a lot of variability in baseline. I would normally not start treatment there, but I'm just going to be aware there's a lot of variability. When I did the treatment, I can show that it made a distinct change. So the presence of the treatment appears to be related, but again, the weakness is it's not a functional relationship. I can't demonstrate it. It could be, but I can't argue it until I have more convincing data with prediction, verification, replication. So the strength is it shows a change. The weakness is I can't argue it's a functional relationship. So here is the same thing, reversal, withdrawal. So there's a return to baseline. Here, baseline's low, treatment changes the level. I pull up the treatment. Now I can say, once again, here's a functional relationship between the presence of treatment and the absence. It goes up when and only when I treat. So that's the very basic design. The disadvantage of this design is I have to stop treatment for a behavior. I've got to pull it out to prove the functional relation. So I want to try to find it. There are other designs where I don't have to pull it out. This is just a good way to show there is a functional relationship. One way to solve it is to go to a multiple baseline design. A multiple baseline design is still a two-phase A-B design. The multiple baseline means there's more than one baseline. It's still a single element because the element is still one single treatment. So if this is, with a multiple baseline, I could have 3 different behaviors for the same child, or 3 different settings. I could treat the child at home, at school, and in the community. Or I could have 3 different students, 3 different children. I could have Billy, Bobby, and Janet. So with a multiple baseline, I start out by collecting the baseline, and then I start my treatment. When I see I have a fairly stable baseline, I start treatment, and I see it's like an A-B design comparison that in fact it did change. Now, I can see the second baseline for the second student, I let that continue to run. I did not treat that child yet. So this shows my prediction that without treatment, it won't change. And that, sure enough, that helps me confirm the prediction. But this shows, because it did change, I can talk about the idea that, look, it did change when I did it. So there's my comparison, it changed. For my verification, I start the treatment on the second student. I wait to have a delay here. I start it, and now I can verify that it changed when and only when I started treatment. And now, for the third student, I let the baseline run even longer to show that it didn't just change arbitrarily. And when I show there's my prediction that it wouldn't change without treatment, there's my replication that I have now made that same effect happen. So I verified it, verification, and I have replication. So now I can argue there is a functional relationship between the presence of the treatment, the independent variable, and the behavior, the rate of behavior. In all 3 cases, in this demonstration example, it went up. The advantage is I did not have to pull out the treatment. The disadvantage is I spent a lot of time collecting data. I didn't really need all that data. That's a lot of data that I'm getting, but not doing much with it other than making my argument. So the solution to that is to take a multiple probe design, which is a multiple baseline design, but rather than collecting a ton of data, I'm going to probe to see behaviors to begin with. I'll wait a while to see in case the world changes it. I'm going to probe again, and then I'm going to start treatment. So when I do that, I see that the behavior goes up. I wait for the second student, and I save all the time collecting data, and I collect a couple of probes, and I see it didn't change on its own, and now I put the treatment in, so now I'm replicating that it changed when and only when I put in treatment. The third one, I waited even longer. There's the prediction that it won't change, and this shows me it didn't. So there's my baseline logic. There's the prediction. There's the verification of change, and there's the replication of change. So baseline logic lets me say, once again, I can show a functional relationship between the presence of treatment and the level of behavior. The independent variable, it changed when and only when I put the independent variable in. So again, a 2-phase design. It has more than one baseline. I had more than one data point, so I call it a multiple probe. I probed more than once. Now we have another design that is called a multi-element because I have more than one element, more than one treatment. In this case, it's alternating treatments. And what the advantage of this is, I don't have to necessarily get a baseline. And instead of only taking all this time to find out if stickers work for this child, I can test 2 things. And what I'm doing with multi-element, this one, more than one treatment, I'm going to alternate. I'll try stickers. I might try stickers here, or praise here, and then stickers, and then stickers, and then praise, and then stickers and praise, and stickers and praise. So I alternate back and forth with my sessions. I do fairly rapid changing back and forth. And I collect the data for each of these conditions. This one is be in your seat, get a sticker. This is be in your seat, get praised. And I can pretty quickly look at this and see the presence of the treatment of A produces a higher rate of performance, a higher rate of behavior compared to the treatment of B. B gets a lower rate of performance. So I can look and see, in this case, this example, there's a nice clean difference. If they start to overlap each other a lot, it's not clear one is any different. With this particular example, I'm going to argue the presence of treatment produces higher rates of responding, and this treatment B has lower rates. Now, if I want a higher rate or lower rate, I know which treatment to use. And I'm showing a functional relationship that it changes, and it's different when and only when I have a specific treatment in place. Again, multi-element because there's more than one element and I'm doing two treatments. Another design is called changing criteria. And I have this on both of these two graphs here. So if I start with the behavior, and what I'm doing with the changing criteria is I found out the child will perform to get stickers. And so I make the child give me at least two math problems, work two math problems correctly, and then I reinforce it. And I do that 3 times. Now what I want to do is change, I want to get more math problems than just 2 correct. So I'm going to change the criteria that now the child has to get at least 3 math problems correct to get the reinforcing. And that's what the data shows me. This is when he met criteria. So the behavior's in the repertoire, but I'm shaping the number of correct responses. And when I show that, and this is, there's baseline, here's like phase 1, phase 2, phase 3, phase 4. You could call it B, C, D, E. You could call it phase B1, phase B2, phase B3. It's the same treatment, but I'm changing the amount of requirement to get the reinforcer. And I do it again, and notice it, and then I want 4 correct math problems before I reinforce it. And then I get 5 correct math problems, and I can change the length of the sessions. Here I get 3 data points, here I get 5. So because it looks like an increasing trend. But I notice that the changes are pretty much in line with my criteria. So it's a changing criteria, and I'm able to get more and more correct math problems. Now maybe what I want is to get a longer duration. If this is a child reading, and he's reading but not reading very long, I can set criteria, read for 2 minutes, then read for 3 minutes, now read for 4 minutes. So I can take some parameter, one of the dimensions of behavior, the occurrence of math problems of frequency, or I can take the duration of the behavior of reading, or I could take the intensity of the behavior. If I have a child reading out loud and he reads so softly the teacher can't hear him, he has to read loud enough to be heard from 2 feet away to get the reinforcer. Then the teacher moves back to 3 feet away. Now he has to increase magnitude intensity of vocalizations and read louder. So I can take this design and gradually increase the property of the response. More responses, longer duration, more magnitude of volume, and I see the increasing, and it changes when and only when I change the criteria. Now, if someone says, well, that's an increasing trend anyway, my control is in this condition, I will lower the criteria. And if it was an increasing trend, it should continue to increase. But when I lower criteria as my control condition, the child performed lower. So that shows the presence of treatment, and the criteria is what's affecting the performance. That's changing criteria. Now I can do the same thing for if I wanted someone to do less behavior. If someone wanted to stop smoking, I could get a baseline and tell them, you're smoking 50 cigarettes a day. We have to smoke 45 a day or less to get criteria. Let's say they're getting $5 for each cigarette less that they smoke. And then I change criteria again. So I can change the direction whether I want more behavior or less. It's examples of a changing criteria design. It's the single element is still the same reinforcer. It's not not 2 treatments, it's a single treatment. But it's another way to show a functional relationship between the criteria for the performance, and it's a way to increase or decrease a particular rate of responding. Now, the next design is called a component analysis. And this component analysis comes from a package. You have a behavioral package where you can put together different components. I might tell the teacher, okay, try appraise, try high fives, try stickers, just everything. Do what you can to get the kid to behave better. So I put together a behavioral package. And over here I have, in baseline, I have a low-level performance. And here I have, just say that, we'll say I just had the presence of, maybe I was testing the praise. And I see I got a lot of responding with praise, and I compare it to baseline. In a component analysis, I have to compare 3 conditions, and I have to balance it. I need baseline compared to the treatment of Y compared to baseline. And I can see baseline is low, the presence of Y is high, baseline is low. So I can say this is like a reversal design, an A, B, A. And so it's high when I have this, and it's low when I have this. And I can see the effect of Y. Now, if I tried 2 elements to say praise and stickers, so that's Y and Z, I can't compare Y baseline and YZ. That's not a fair comparison. I've got to move over and compare baseline to YZ to baseline. So now I see baseline's low, YZ produces a high rate of responding. Baseline is low. I can make that component analysis of the components of Y and Z. This is a comparison of Y only to baseline. The key is you have to bracket each side of your main condition. You've got to bracket it to show that you have a balance. Next, I can go to baseline, and I have there's baseline to YZ. Now I want to test YZ, the combination, with just Z. So I can't compare baseline to YZ to Z. Those are three different conditions. I've got to have YZ to Z to YZ. And there I see when I have YZ, I get a high performance. When I have Z, I get no performance. When I have YZ together, I get a high performance. So what I could conclude from this component package, in this case, I had two things. I had a Y and a Z element. We'll say it was praise and stickers. So I see that Y alone produces what I want. When I add Z to it, I still get a good performance. So the question is, do I really need to have a package? Can I save myself some time, effort, and be more efficient? And by comparing YZ to Z alone, I find out Z really has no impact whatsoever. So if I got a teacher that says, I can't run around and give stickers and high fives and praises, I need to be a simpler package. This is a component analysis to tease out which component is going to have the biggest bang for the buck. And in this one, I learned I don't even need Z. The performance is the same. Here's another thing where I do the same. I take baseline, I put in Y, I get about 50% responding, I compare it to baseline. So my component analysis is baseline to Y to baseline. And now I'm saying, look, it changes only when Y's there. In the absence of Y, it's low. And now I can't compare Y to baseline to Z. That's not a fair, legitimate comparison. But I can compare baseline to Z to baseline. So I compare those three, and I see that Z produces about half of what I want. And now I cannot compare Z to baseline to YZ, but I can compare baseline to YZ to baseline. And now I can show when I combine Y and Z, I get 100% performance. So I can compare baseline to YZ to baseline, and I compare YZ to baseline to YZ. And now I conclude that I get about half of what I want with Y or Z, but I put Y and Z together, and I get 100%. So in this case, if I want a higher performance than 50%, I'm going to use this package. And this is how I analyze the components of my package. So a component analysis is a behavioral package, and you want to tease out for efficiency to see what's actually contributing to the functional relationship, the presence of what affects behavior how much. Here's another sample of the idea of a way to tease out components. I've got a problem behavior occurring, and I have a hypothesis that if I play music, maybe that'll calm the room down. So to calm this child down. So I put in music, I compare baseline to music, an A-B comparison, and I see that it looks to be lower. But I really can't make any functional relationship arguments because it could have gotten lower anyway. So now I put in video game. And when I give a video game treatment, I see the behavior really drops. And when I compare baseline and music to video game, I see it's going down, but I cannot yet say there's a functional relationship. I use a component analysis, and I compare music to video game to music. And I see with music, it's at about 3. And with video games, it's about 1. So this is my fair, legitimate component analysis, music to video game to music, and I can say there's a functional relationship between the presence of the video game and the level of responding. Now I can do that again and move over, and I can just check the video game compared to music to video, and I get the same results. So I'm replicating the effect that video will produce a lower result. I saw that over here, but I did it again just to check it, and I can come over here again, but now I've got music and I've got video and baseline. So this is not a fair comparison. I've got to go over again. I can compare video to baseline to video, and I can see that video indeed produces a lower rate of responding than just baseline. And I can compare baseline to video to baseline. That's a fair component analysis and get the same conclusion. Video produces a lower rate, and I can compare video to baseline to video. So a component analysis, you have to balance what you're comparing with something the same on each side compared to the middle to see, is there a functional relationship? Did it change? When and only when this condition's in place? Now then another design is called parametric measure. This is not the best graph, so I'm going to explain it a couple ways. The idea is that parametric is going to be many measures of the independent variable. In other words, when you go to the doctor, if you have an infection, he's going to give you some medication and give you maybe 20 milligrams of some antibiotic to try to knock down that fever, to knock down that infection. So he's going to try 20 grams, and if you take that for 2 weeks and come back and you still have the infection, he might bump it up to 30 milligrams. So with behavior analysis, when we're trying to find out how much of the reinforcer do I need to affect the behavior to get the level that I want. So here in this edibles, what they were doing was comparing, here's in the, here's an FR1 reinforcement schedule. So this is one condition I'm going to compare, and they put in either small edibles or large, medium edibles or large edibles to see if the amount of edible that they're giving the person for, we'll say, not doing the problem behavior, does it make a difference? And we can see that all three of these, they bounced a little bit up here, but they pretty much all three had a similar effect. So it's not the best example, but I just want to show that you can compare how much of the reinforcer. What if I give an M&M? What if I give 10 M&Ms? What if I give a bowl of M&Ms? So if I have the different amounts of my treatment. This graph will let me, I'm going to go ahead and use the change of criteria graph, but I'm going to use this data and explain the parametric measures. So when we looked at this before, we saw I had the same amount of reinforcement. I required more behavior to get the reinforcer. This time I'm going to use the same graph to demonstrate a parametric that I need to know how many stickers do I need to get good performance. So if I give the child 2 stickers for good performance, I get this level. If I give him 3 stickers, it turns out I get more behavior. If I give him 4 stickers, I get more behavior. I'm trying to find out at what point can I get the maximum performance for the best reinforcers. I can't run around the room giving kids reinforcers and praise and high fives all day long, but I can sort of test with this design how much praise how many times per 15 minutes do I have to praise. And if I find that the more I praise, the more I get, at some point this line's going to pretty much flatten out. So if these were to all stay at this level from here on over, I would see that right around 6 or 7, I get about as much performance I'm going to get. So pretend this didn't go up and it just sort of stayed right about here. I would find out with my parametric mini measures of how much of the treatment do I need, how many milligrams do I need to knock down the fever, how many stickers do I need to get the children to give me the most I'm going to get. At some point, they just can't keep improving. They're going to eventually flatten out. So a parametric measures could look very much like this. The difference is this is the amount of reinforcers I'm varying, and with the changing criteria, this is the criteria I'm asking for the behavior. So they are very different concepts that you're testing, the amount of reinforcement versus the actual criteria for performance. In some of our cases, we measure the number of trials it takes for the child to reach criteria. If we're trying to teach colors and discrimination of red and yellow and green, we want to set a criteria to get it right 9 out of 10 times. So criterion-based measures are going to be one way to try to graph to see what we get. So let me back up a little. This chart that I built is my experimental design chart. I will email this to you, and you'll have it for your studies for down the road. And as you run into the chapters, you run into things on experimental design, you're thinking back about these very basic premises. So you're going to want to look these terms up and be sure you know them, recognize them, read up on experimental design. And these are the most common designs you're going to see in our field. These were basically all made up and discovered as ways to answer the question, how do I show a functional relationship between the presence of the treatment and the performance and the behavior? Now, there's nothing magic that says you can't combine them. For example, I could take the alternating treatments design, take this, and I could put it over here in the back end of a baseline. I could take a multiple baseline design, and I could add another phase, and I could go to, if I know that this treatment is getting a certain amount of behavior, my question might be, what if I tried something else? I don't have to run a whole nother experiment. I'm allowed to take anything that I can think of, which of these would let me see and show that. So if I did that and put that over there, then I could show that, gee, this was getting me a high level of treatment. This was treatment A, and this basically looks like it's still there. If I tried treatment B, I would find I get a low level of performance. So one of the items on your task list says use combinations of experimental designs. So this would be how you would combine an alternating treatments You had a single element design here. You decided that I've got pretty convincing data. I wonder if something else could work. Maybe these stickers are expensive, so I can find something that they give away free at the grocery store somewhere, and I could try another treatment to see. And if I got the same performance, I could maybe save some cost and be more efficient. So these are common designs. These are what you're going to see in the literature. My point is, one of the things we're trying to do is understand how to demonstrate experimental control so that it changes when and only when I do my treatment. If it's changing when I didn't do treatment, then some other variables are kicking in, and then maybe some extraneous variables, some confounding variables, something else is happening. It's a rainy day. Uncle Jack came to town and he's visiting, so the kid's excited about the company, things that aren't part of my treatment, and they're affecting how the performance goes. So I'm alert to, and you want to be familiar with the concept of confounding variables or extraneous variables. They're things outside your experiment. Because we're trying to show experimental control, we're trying to show that it changes when and only when I do my treatment.